Very excellent, thank you. Then please welcome Dr. Stephen Blenkinsop. Over to you, Stephen.
Hi, Irene. Thank you very much for inviting me. I'm just checking everyone can hear me okay. Can you hear me? Yeah.
Yeah.
Yeah, all good. Yeah, my first challenge is actually share my screen, Zoom. It's something I got really familiar with during the pandemic, but then since we've come back to face-to-face, less proficient. So let me just see if I can do this right. So can you now see the slides up? Yep. Excellent.
Beautiful slides. Yeah.
Yeah. Okay. Yeah. I'll crack straight on then. So yeah, thank you for the saved me doing a little introduction of myself, which is always good. So yeah, the title of this was the weather forecast for the coming decades. And I'm going to really focus on rainfall change, although obviously in the discussion afterwards, if we want to talk about sort of wider issues, quite happy to do that. But primarily going to focus around rainfall because that's the research group I'm in is actually the water group. So we do a lot of work looking at floods and droughts. I've got work with various hydrologists, engineers and hydraulic engineers and people like that who are interested in how we adapt to those things. And I'll touch on some of those issues later on towards the end of the presentation. And I've just put this up here. This is Storm Henk. So we're getting familiar with storms now. I don't know whether they're going to run out of names very soon, but we're getting more and more exotic names. So this was the one back at the beginning of the year, and you can satellite, or that might be probably more radar image there from the Met Office on the left. And the slide says there that saw flood warnings across England, Wales, and Scotland. Lots of properties flooded, and I think it was about 150% of the kind of winter period rainfall in some parts of the country within just that one storm. And some of the impacts of these events are actually quite significant and not very pleasant. The image I identified on the internet that was taken, as it says there, I don't think actually, I can't remember where I said that was taken from, but it's actually a location where all the water went into the sewers. And in this country, we have a lot of combined overflow and storm drain and sewer flooding. So here, all the water piled in and mobilized actually all the sewage. And what you can see in there, that brown water is actually water from the sewer system as well. So it becomes overwhelmed. So some of these floods we see are particularly nasty. That was in January. But I just wanted to start with just a general introduction on sort of where we are in our understanding of climate change, talk about some of the evidence and the attribution of that change, what the evidence is, how we know that humans are responsible for this change. So that's going to be the first few slides I'm going to talk about. This is a very famous graph. Many of you might have seen it. This is called the hockey stick graph. So this is going back, you can see on the right there, we've got the present day going back 1,000 years. And this is the reconstruction, in this case, of the Northern Hemisphere temperature. So the red lines that you might be able to see at the right-hand side, they're actually the temperatures that we've measured from, they go back to the sort of 1900s, where we're global series from these thermometers. And then going further back, those blue lines are actually reconstructed from other sources, things like tree rings, pores and things. So you might be able to see the sort of grey envelope around those. That's actually the uncertainty in those measurements, because obviously if it's not directly measured, there's a lot of uncertainty around those. So you can see they aren't as precise as obviously as thermometers, but you can see the long-term historic variations in temperature from that. And this has been reconstructed of different data sets. It's been a highly contested graph. And then just focusing in on there, this is the actual one of the global temperature record we would call the sort of instrumental period that you can see there, focusing on that last part of the graph, showing since 1860 that we've seen increase. So that's really the first line of evidence pointing to a changing climate, our record. And that doesn't just come from temperatures, it comes from things like sea level rise, things from extreme weather, from rainfall data, from sea ice. So different indicators that are pointing in the line of this evidence. But it's not just our observations, it's consistent with physics. So you will have heard of the greenhouse effect. So this is the natural effect of greenhouse gases like carbon dioxide in the atmosphere. Actually when the radiation comes into the Earth, it heats the Earth's surface, but the Earth then re-emits that as long-wave radiation, which is the type of radiation these gases can absorb. And obviously, that's perfectly natural and it makes the Earth habitable. But with our burning of fossil fuels, particularly since the Industrial Revolution, that's actually increased the amount of CO2, and we're increasing other greenhouse gases as well in the atmosphere. So that's been known as the enhanced greenhouse effect. And, we can measure as well, just as we can with temperature and rainfall, we can measure CO2 in the atmosphere as well and reconstruct that further back. So there's a good physical basis for anthropogenic climate change as well. The third evidence that also points to this effect is what we distribution, and this comes from climate models, and I'm going to talk about climate models very shortly as the main tool that we get for looking into the future. But just that third graph on the right there, you can see two main lines, a green one and a sort of browny yellowy one. So if we look at the green one first, that kind of hovers along, we've got on the vertical here, we've got degrees temperature change too. And what we can do is we can run these climate models that simulate the global climate, and we can put different factors in, and we can take different factors out and use that as an experiment. So that green, we just drive the model with what we've observed from natural factors, so things like solar variation, things that we do know affect the climate, but are just natural, things like volcanic eruptions and natural variability. So you can see there, when we drive the global climate with those factors, so you get lots of variability, but it doesn't produce any sort of long-term change. But then if you look at the sort of browny yellowy line and envelope, what you can see is that's when we add in what we've observed in terms of greenhouse gas concentrations, our emissions that we've added. And then when you put those into the model, you can see there we actually reproduce the observed warming, which is represented by the black line. That's essentially the same graph as you see in the middle there. So that's our observed temperature in black. And then the brown one is what we get from the models, but only when we add in the sort of human influence. So that's our third line. And these are all sort of consistent in pointing to anthropogenic change, the observations, the physics, and these attributions. But we can talk about those maybe later on. So that's temperature. And I said I'm going to focus on rainfall. So why does that change in temperature? We often see in the media, we talk about global warming, but there are other effects, obviously. And I'm going to talk about rainfall. So the key headline is that this change in temperature can actually drive an intensified water cycle. And statements there that I pulled out from the IPCC's 6th assessment report. So this is the UN body, the Intergovernmental Panel on Climate Change. And one of their roles is periodically, every 6 or 7 years, they produce a review. There's a team of scientists get together and they review of all the literature that's been published and essentially summarize that in 3 very large tomes. So I've just put some quotes in terms of rainfall change. And so you can see the frequency intensity of heavy rainfall events have increased over most areas for which we've got data. And they're saying that human-induced climate change is likely the main driver. And they use lots of language like likely and certainty in the report. And you see there, a warmer climate in the future will intensify very wet and dry weather and climate events, implications for flooding and drought. So I'm going to talk about that in the 3rd section, I think, of this talk. So what is the basis for that? Why do these changes in temperature cause changes in rainfall and changes in the water cycle? Well, of course, higher temperatures can produce greater evaporation, so that's intensifying that cycle. But also, as air warms, it's a physical property of gases. As gases warm, and the atmosphere is just a gas, its holding capacity can increase. So as the atmosphere is warming, it can actually hold in it more water. And there's a piece of physics called the Clausius-Clapeyron. Air can generally hold around 7% more moisture for 1 degree of temperature rise. So people are using that as a proxy for then what will happen to the intensity of extreme rainfall. It won't exactly be 7% because that's just the moisture holding capacity of the atmosphere, but rainfall can depend on other factors as well. But there's been lots of studies, and this is just a graph from a paper I published some time ago for one normal location in the UK. You've got temperature going across the bottom there, and you've got extreme rainfall at different temperatures. And there is a sort of relationship that roughly follows this 7% pattern. It's not exact, But there's been lots of studies globally about this, and we observe it, but it can actually exceed that in certain conditions as well. You can't just use 7% as a predictor for change. There's actually lots of other factors, but it's a physical basis for expecting these changes in intensity. And we'll also see shifting weather patterns as well. Some tracks can change and other factors as well. So that's kind of the physical basis for how climate change. So what we observed, I'm going to on the UK. These are just some headlines. Every year, the Met Office produces a state of the UK climate where they review the kind of the weather of the past year, but they also put that in a historical context in terms of change. So this is the review of the 2022 climate, 23 at some point this year. So you see some headlines there. They've concluded that the UK climate is getting wetter, and 5 of the 10 wettest years for the UK have occurred in the 21st century. If they take the most recent decade, and you see there they're defining that as 2013 to 22. So those winters in winter period only have been 10% wetter than the standard climatology, looking at 1991 to 2020. And if you look at another reference period a bit further back, it's 25% wetter. So you can see the time series of that at the top on the right. This is winter rainfall, showed with the blue line there. So that's the year-on-year. Point of rainfall is it is very, very highly variable, which makes picking out these long-term trends more difficult, and also it's less reliable. It's much more easy to do with temperature, because rainfall has more decadal variability as well. It's influenced by lots of different factors. But you can see the dashed black line there's a sort of smooth series showing the overall upward trend here. We've got sort of total winter rainfall amount on the vertical axis. In terms of summers, you can see there summers have tended to become a little bit drier. So again, the latest decade is slightly drier than the 30-year baseline I referred to, and 6% wetter, in fact, than a baseline further back. So it's much less clear position in terms of summer. And you can see that in the sort of figure just below there, just below the winter one. There's no real clear, easily identifiable pattern there. There's lots of sort of multi-decadal variability. 2009 seasons have been in the top 10 wettest in the UK series. So you can see there, we've had a series of very, very wet winters, and a couple of also wet spring, summer, and autumns. I've already mentioned it's difficult to identify trends and long-term patterns in rainfall compared with temperature because of this inherent variability in temperature. But the thing we're really interested in, the thing that has impact, is not sort of total rainfall or average rainfall, but it's actually extremes. So scientists do a lot of analysis of extremes of climate. And the graph here you can see is a time series, again, not going back as far this time, going back just to the 1960s of what's happened to extreme rainfall. And this is the number of days exceeding what we call the long percentile. So it's kind of, you define an extreme event by the distribution of rainfall. So you pick the top 5% events, and that's your threshold, and then see what frequency they've occurred with each year. So you can see that there's been more kind of in the most recent decades compared to a little bit back. And, we can use other measures as well. Here's a count of days of stations where they've identified more than 50 millimeters in a day across the UK, and you can see here a slight tendency for them to be more. So they've concluded that we've seen increased intensity of rainfall in the past decades, but also more rainfall events in the most sort of recent period. But again, much more difficult to attribute this to climate change than temperature. But there's a new emerging sort of branch of climate science called attribution. Here's an example. I'm going to give you an example of that. This is Storm Desmond. Some, I think, photograph from Carlisle, Lancaster there. The morning after, you can see what that's caused. But I mentioned attribution in the slide where I was talking about how we causes of climate change, and they can actually do that now for individual events. So what they do is they can run these climate models lots and lots of times, greenhouse gases in there, without these increases in greenhouse gases, and then run these climate models again lots of times, but with greenhouse in there. And what they can do is, okay, how many times in each of those sets of experiments do we get an event like Storm Desmond? And this is referred to as an event attribution study. So what they can then say, you can see a conclusion that came out of one particular study for Storm Desmond, the level of extreme rainfall is roughly 60% more likely because of climate. So essentially saying, we could get these events anyway, but we're loading the dice, increasing the probability of seeing these by putting our greenhouse gases into the atmosphere, which is warming it and which is increasing the moisture holding capacity. So yes, there's lots of historical precedent events, but we're loading the dice, we're increasing the likelihood of getting them. I'm going to move on and talk about and how do we tell what the future might look like. And I mentioned climate models, so I'm just going to say a little bit about those. As I'm sure you're aware, it's very complicated. It's not just the atmosphere, but land surface. There's lots of complexity going on there. There's evaporation, there's radiation, there's transfers of energy and moisture across components. So we represent that complexity essentially in computer models. So these are just physical representations of these processes represented by maths in complex computer code. Just included a snippet of there. It's actually millions and millions of lines of code, and they run these on supercomputers, not sort of the types of thing we have at home or in our offices, but these are big things that fill a whole sort of and they essentially structure the world into of grid squares. So they simplify it because of the amount of computations it has to do. They discretize the world into these series of grids. Model, if you're trying to represent the whole globe, they're typically sort of 60 kilometers by 60 kilometers. Now that imposes some restrictions, as I'll mention about the information that provides. These models, so these global models are called general circulation models or global climate models because they represent the whole globe. GCMs is the acronym. And Wilhelm Bjerknes, I think that's how I'm entirely sure. So he was Norwegian who did a lot of work on meteorology, and he realized that you can describe the physics of the atmosphere and the dynamics by equations, which form the principle of a lot of modern day weather forecasting. And these are the same principles that go into these climate models. But of course, as I mentioned on the previous slide, these models are simplified in the sense that they're discretizing the globe into these sort of very coarse grid cells of 60 kilometers. Now, some of the processes in the atmosphere actually happen on much smaller scales than grid cells. So if you think of storms you might have experienced, particularly sort of summer thunderstorms, they can actually be just kilometers or less. They're very, very localized. So some of these are actually really, really simplified in these global models represented by much simpler equations or parameters. And this process that produces thunderstorms is what's called convection processes that isn't properly represented in these global models, but I'll talk a bit more about that. So you can see here how we do a typical climate experiment. So we'll run what's called a control sample. You'll run the climate without any what we call perturbation, without any changes in greenhouse gas emissions, and you'll analyze how the climate evolves. But then you'll have an experimental sample where you'll run, but you'll make some assumptions about the future, and these are called scenarios. So here's just a simple example of that. So we've got a line across there going across in time, and what they're showing is how much carbon dioxide we're going to emit globally. So these are just different storylines, if you like, about what might happen to global emissions based on technological developments, global geopolitics. So you can see some of the names there. They're not given very explanatory names, but basically, if we just focus on that high one, the red one, and the blue one at the bottom, you can see the high one there. I put this little scenario in which we continue to emit lots of greenhouse gas emissions, lots of sort of fossil fuel power generation, whereas compared with the blue scenario, that's a future in which, say, we invest a lot in greenhouse gas, in green technology, and make lots of other sort of green developments in society. Now, it's a very simplified, these are very complicated, just a simple way of looking at it. But these are just different storylines, in essence, of what might happen. We don't know which of these we're going to follow, so we can run the model under these different types of story. And these can tell us then, okay, under a high emissions scenario, under that sort of storyline, what sort of change will we see? And under a lower emission, you might see a different future. So I'll give you some examples of this for the UK. But I'm just going to talk about this problem of scale as well. You're interested in flooding, maybe in a city, or in even, you know, if you live in a rural area, you might want to know how is that going to affect me. And these really coarse models don't really sort of cut it. So you can see another example from a radar there. So the red and the yellow areas are real intense areas of rainfall. But because the climate models, as I say, discretize the world into these grid cells, you can see there, that's how a climate model would see that particular location on and off. It loses a lot of the detail because it's just smoothing things out because of its resolution. So that doesn't really let us see those high intensities that might point to things like flooding. So there's a gap between actually what we really need to address some of the consequences of climate and weather extremes and what the actual models provide us. And I saw someone put in the chat already there, climate downscaling. Well, this downscaling refers to just a range of techniques that we can use to go from this very coarse scale down to much information that's actually very, very useful. And I'm just going to give you one example, downscaling, but there's lots of different ways of doing it. So one way is we've got these global models that I say have these quite big grid boxes, how the Earth is represented. But if you're interested in the effect of climate on a particular area, so here we've got an example, say we're interested in Europe, well, what they can do is they can build a model over that region, increase the resolution, so make those grid squares a lot smaller and add in that detail. That requires more computing power because of the calculations you need to do. But by limiting that to a limited area, then you can add in that spatial detail. So here's a map just occasion of what rainfall looked like over the UK, the very blocky nature of the rainfall pattern when you have these models at 60 kilometers. But I'm just going to toggle through that information. You can see what happens here. And the grid squares much smaller, 25 kilometer, 12 kilometer, and finally at 5 kilometers. You can start to see how increasing the detail in that model lets you better pick out some of the details, so you can then actually use it more for more local scale analysis and impacts. And the sort of state of the art of it is we can actually use now the weather forecast type models, which are really detailed. We can actually use now those type of models, those levels of detail in climate change experiments over very particular limited areas. So you can see here, we start off with a global, then we might focus on Europe, and then we might have a retail model over a particular area of interest. And here's just an example from Boscastle in the southwest, which had a big, very, very localized storm, the sort you can see in the top image in the middle there. And the top sort of figure of the map is the radar for that. So again, those high intensities are the reds, purples, and there's a bit of gray in there, really high rainfall. But below that is what that storm might look like, a climate model. And you can see how you go from 12 kilometer, these very relatively big grid squares, down to 1 kilometer. You get that detail in, you can actually start to better model and better reproduce the real type storms we see, these very, very localized storms that produce flash flooding. So this is kind of the state of the art for particularly for type things. So I'm just going to talk about giving you a very brief introduction of sort of climate models and the state of the art. I'm just going to talk about how might UK rainfall change in the future. So, you know, what might we expect here? So the projections for the future climate provided for the UK Met Office, and they come from a project called the UK Climate Projections, and these are produced every, well, it varies, but sort of 7 or 8 years. There's a new latest technology. The latest version, it says there, were 18, so they're called UK CP 18. And they use the latest models that were available at that time, used updated weather observations, and they've produced a range of different products at different resolutions. So you can see it, hopefully see in the slide there, I've got 3 columns. One is global, They produce these model run simulations at these relatively coarse grid squares that allow us to talk about large scale global change. Then they produce these more detailed resolution projections over Europe, where the grid squares are 12 kilometers, and that lets us say things about temperature extremes or river flooding, winter rainfall extremes. But then they've produced these really highly detailed sort of weather forecast resolution models called local, and this can give us information on intense summer rain, those types of storms that affected Boscastle, those really localized storms that produced flash flooding and do cause us lots of problems in the UK. Let's talk about things like the urban heat island and really strong windy gusts as well, that you need this kind of level at detail at. But the point is that they're providing a range of projections at different scales for different applications. And they've also produced projections of sea level rise as well, which you can find this information. It's all open access on the internet. So what might we expect then for climate change in terms of rainfall over the UK? So some of the headlines from UK CP18 that we would expect winter precipitation increase significantly. So I've just pulled out some maps here now. There's a lot of maps you can get out of there for different sort of scenarios. So I've just a selection. So here we've got two scenarios, which are the two rows. So the top row is what might happen, what we think could happen to rain under that high emission scenario in the future if we don't cut back on greenhouse gases. This is what the models say UK look like, whereas this bottom row is actually a more green future, reduce our emissions. So what do we sort of see? Well, if we just look at the sort of maps in the center of the sort of columns, what we can see there's in the top one, we actually see increases that vary around the country, but you can see large areas showing a 30% maybe increase, 30 to 40 in some regions. Whereas if the lower emissions, by reducing those emissions, we're actually seeing much lower changes. So you can see in the lower middle plot, we're actually seeing over a lot of the UK sort of an increase in winter rainfall of around up to 10%. So that's one sort of set of projections. So what are these other side? Well, climate models have a degree of uncertainty, and I'm not going to sort of talk about this in detail during my presentation. We can perhaps talk about this afterwards, but run the climate models lots of time with slightly different parameters that refer sort of incomplete understanding. So even within one emission scenario, so if you go across, say, the top row, so even under that high emissions, there's some worst and sort of best cases. So for the high emissions, the worst case scenario is that top right plot there, where you can see sort of 40, 50, maybe even 60% increases in winter rainfall, which is a lot. So that's relatively, that could happen, but it's kind of giving uncertainty information process. It's saying there's a chance that it could be as bad as this, and how you treat that uncertainty is. In terms of summer, I've already alluded to this. We're expecting decreases in summer rainfall. So again, at the top of that graph set of maps there, you can see the high emission scenario. So we're seeing in the south, what does it look like, a 50 to 60% reduction in seasonal rainfall, decreasing as we move north. But then that's obviously reduced in the lower row of figures, where we see much smaller reductions. But again, there's a worst case scenario here because we're talking about reductions. The worst case is the left-hand column. So you can see in a worst case scenario, that top left figure, it's showing sort of 80% reduction in summer rainfall over that southern part of England and South Wales as well. So again, that's a low probability, but it is the worst case scenario. So that's just what's suggested to happen with summer precipitation. But what might happen is that when it rains, there could be more intense storms. So the rainfall, in a sense, might get compressed into these much more shorter events. And there's some information I can give you that. So I'm just going to talk about extremes, and first sort of daily extremes. Now I'm going to try and there's lots of detail in this, so I'm just going to pick out some points to take away. So on the graph on the left, what they've done in this analysis is they've taken global warming. So if you go across the bottom axis, you can see what they're showing: 1.5 degrees of global warming, 2 degrees, up to 4 degrees of global warming. And on the vertical axis, so these lines are showing per year where we get what they call high impact rainfall that they've defined by. So if we just look at this solid blue line, the top one, this is just showing over England and Wales. And you can see what it's saying is, as global warming increases, we actually start to see more of these extreme daily rainfall events. So you can see here, the 1.5 degrees, it increases if we don't reduce our emissions compared to 4 degrees of global warming. So I mentioned this drying out in summer, and this is another example from the same paper. And here they've just measured of drought intensity. So don't worry about the sort of magnitudes, what these mean. But this top left map showing the observed drought intensity. So the darker is the more intense drought. And you can see here we've got, again, under 1.5 degrees in the next figure, relatively little change. But as we increase to 2 degrees and 4 degrees of global warming, particularly down of the UK and parts of the southern England, we're seeing an increase in drought intensities. So I did mention some of these summer storms, and using these sort of very detailed weather models, people have produced these simulations of what might happen, what percentage increase we might expect in these very, very, very rare rainfall events. So here again, on the left, we've got a plot of the medium estimate, kind of moderate estimate, and here we've got a higher estimate, a kind of lower probability, but kind of more, again, more of a worst case scenario. So there's slightly different color scales, so don't sort of directly compare the color scales on these, but you can see if we look at southern and eastern England here, this main area, sort of going from north to sort of Devon and Cornwall, you can see it's showing a sort of roughly around a sort of 15 to 20% increase in the intensity of these short duration intense storms. So think of it as like this thunderstorm intensity. But the high estimate, so this high risk, low probability, but worst case, here we're talking about a 30 to 35% increase in this part of the country. And you can see in this case, the percentage increase is getting higher as we move further north. So this, potentially could lead to increased flash flooding, because this is the intensity of short, intense, stormy. And again, just an inset to that map. This just to show you the kind of resolution that we're talking about. Information that's over kind of the northern part of England and southern Scotland. So what might the impacts be of these changes then? So this is a hopefully nicely helpful figure from the Met Office, and quite often when we talk about it, doesn't actually tell us what it means to me and to you and to society. We the center of that, we've got talked about emissions of greenhouse gases, things that cause changes to the climate that we're making. But then there's kind of it's like throwing a stone into a pond, and these are the ripples moving out. We start off with these increasing of greenhouse gases and other changes we're making of land use, etc. And that can wider out there. We start to see more extreme weather, as I've talked about. We start to see changes in the hydrological cycle, and there's some other changes there that are not really going to affect melting sea ice and rising sea levels. So that's changes again the climate system. But then as those ripples go out, they start to impact different aspects of society. So that extreme weather, that changes cycle, that can produce localized flooding, it can scale flooding, damage to infrastructure, and you can see some of the other impacts there of climate change, depending on the hazard that we're thinking about. Risk to supplies, temperature can have lots of impacts on heat stress on human health and on sort of disease distributions. So again, these changes that we're making have these ripple knock-on effects to society. So one of the key concepts that we start to think about then isn't just the hazard, so it isn't just thinking about flooding, but we're starting to think about risk and what that means to individuals, or whether to infrastructure. So the standard definition of risk is a function of the hazard, the flood or the heat wave. So it's as it says there, it's the occurrence of some natural or human-induced physical event that can have some effect on humans or our society or even the natural environment. Hazard. So if you think that, there's a thunderstorm occurs in a place where there's no human economic development or no people living, then there isn't any risk to that aspect. So that hazard doesn't pose a risk. For there needs to be some exposure, there needs to be some people there needs to be some livelihood, some ecosystem that is exposed to that hazard. But there also needs to be some vulnerability as well, and vulnerability is the extent to which either us as individuals or an ecosystem, some piece of infrastructure is susceptible to harm from these types of hazards. So I'll just give an example of that. So again, on the watery theme, think about the hazard, could be current or future flood. So we see an example of a flood there, Northern England. So that's a hazard. So what is exposed? Well, you can see there is an exposure. There's people living, there's their homes, there's transport infrastructure, there's the system, there's electricity distribution system. So there's lots of exposure there in terms of people and assets. And the thing that sits on top is the vulnerability. Now, these hazards and risks are shaped by societal vulnerability. So the picture there on the top right is quite an interesting one. That isn't a photoshopped image. This isn't actually from the UK, this one. And that's showing two neighbouring sort of sets of housing, where one is sort of very affluent. The one on the right there, you can see the white coloured houses with the nice roofs. And on the left-hand side, you can see very stark division there of people living in lower quality, less well-built housing, less well adapted to the. So the risk that we all face from these events is very dependent on that vulnerability. Now, that can be, in that case, the quality of the housing. It could be our health situation. It could be our age. So there are particular communities that are more vulnerable to particular hazards. So that vulnerability plays out in terms of how that level of risk is found. So, for example, think of another hazard, temperature. When we see a heat wave and extreme weather, someone with a clinical pre-condition is more vulnerable. So to them, the risk of a heat wave is greater than to somebody perhaps who lives next door to them, but help the adult. So this concept of risk becomes very important. It isn't just about the hazard. Just some examples of risk in relation to water. So here's, you see some surface water flooding. So again, I think this is in London. So you can see there's been one of these short thunderstorms. It's come down. The drainage system hasn't been able to cope and take that water away, and the topography is here caused an underpass. You can see the effect that that's had there on some cars. Transport system there. You can see the emergency services in the background. And here we've got I think this is a River Trent that's flooded, and you might be able to make out there the rail line. So obviously that's causing a disruption to the transport system that's affected there. So think again then how these might change in the future. Some figures I pulled out just in relation to that rail example. So every 5 years, the UK climate change risk assessment. So it looks at all the hazards and all our infrastructure, different aspects of our society, our health, and tries to assess what the risk is and how that might change in the future. So in the last risk assessment here, you can see some examples from the rail sector at risk of surface water or river flooding. So what you're seeing there is the length of kilometers that are exposed in the first column to surface water flooding. So rainfall in a short period. So you can see there's about 1,500 kilometers of rail at risk. And for river flooding, it's 444 kilometers. And you can see similar figures for the number of stations that are at risk of flooding. Risk, which tell you something about our current, exposure to hazards. But as part of the risk assessment, how might that change in the future? Well, you can see there under a 4-degree scenario, we can actually see 32% increase in risk of river flooding by the end of the century, nearly a 50% increase in railway stations at risk, and again, slightly more for surface water in these intense storms. So that gives you information about, okay, you can start to think, okay, if you're in charge of that rail infrastructure, it starts to tell you, okay, what sort of decisions do we need to do? How can we sort of prepare to reduce this risk? What are they making now? So for the final bit of the talk, I'm just going to talk about what we can do to address these future changes in rainfall. And the thing that gets most attention is what we call mitigation. So this is basically reducing our emissions of greenhouse gases. So that can include things like using low carbon energy, public transport, active travel, but also things like carbon capture and storage technologies or geoengineering of climate. But we've got this global agreement, the Paris Agreement of 2015, that's tasked the global community with limiting warming, if we can, 2 degrees, but preferably to 1.5 degrees above pre-industrial level. So as a UK, you'll all have heard of the net zero strategy, and that's our contribution to this global aim of limiting warming. So we've already seen how by limiting that warming, we can reduce the number and the intensity of some of these hazards that I talked about. So just an example of climate change, how that sort of mitigation effect can affect risk. Again, this is just from the same climate change risk assessment report. This is the number of people exposed to significant flood risk from all different sources of flooding. And the panel on the left is showing the number of people at risk under a 2 degrees warming scenario. And then the 1.8 is 4 degrees. So you can see the depth of the red is indicating the intensity, the number of people compared to present day. So where you've got a deep red color, it's showing that there's a greater number of people compared with the present day. So you can see if we don't do any of these mitigation actions, we're potentially exposing more people to significant flood risk. But if we can limit that warming through our mitigation efforts, then that risk is actually lower. We've got fewer people to that risk of flooding. The other side of the coin, though, is what we call adaptation. Making changes to our society to cope with changes in climate and changes in hazard and increased risk. So in terms of flooding, that might be increasing our sewer capacity. So when we get a lot of rainfall, it can be carried away much more efficiently. It can be putting green infrastructure into cities. So things like green roofs, you might have hold moisture and delay its entry into the drainage system. It could be flood defenses, so hard engineered flooding defenses to protect from rivers. Generally greening of cities, so providing space for water to actually stored rather than enter the drainage system. But it also encompasses adaptation, it encompasses things like emergency planning, so putting plans in to actually cope when there is one of these events. And also behavior change, so it may be that we change our behaviors, change our planning, and don't build, for example, on floodplains. So it's not just about building defences, it's thinking more in the round. And as I said, there's this national risk assessment that is undertaken every 5 years. It's a legal obligation. We're now on the 3rd iteration of that climate risk assessment. And that feeds in the next stage once there's a national adaptation programme in response to that risk assessment, what it's going to do to adapt to these risks. So just an example from that national level assessment of risk. This is the expected damage in terms of millions of pounds from different types of flooding. So surface water flooding, and then we've got river flooding on the right. And the green bars are a low population for the 2050s and 80s, and then the orange bars, higher warming, 4 degrees again for the 2050s and 80s. So you can see for the higher scenario with higher population as well, you see an increased amount by reducing the emissions. We can actually reduce the amount of damages, but under all cases, they're actually higher than the grey bar, which is the present day. And the importance of adaptation here, we can, again, this is the expected modelled annual damage in millions of pounds. And you can see the grey bar there is the present day, is what it would be if we put in additional adaptation to adapt to 4 degrees of warming. So you see it still increases, but actually it's limited compared to our current level of adaptation, which is the dark grey bar, so which is approaching there £4,000 million. reduce our adaptation to below what it is at the moment, so reduce fences, say, and don't make any of those types of adaptation, we'll see that yellow bar, the damages will actually increase. So there's a decision to be made about, what level of adaptation we want to adapt to these types of weather extremes. So just really to finish off, then the last kind of thing talk about is how we can actually do these actions at a local scale, and lots of city councils are doing these risk assessments to identify in local communities, and county councils are doing risk assessments. And there's a very simple sort of framework for doing that, of defining the objectives, identifying what information is available to tell you what risks are, and thinking about what those risks and impacts might be in the future. So you're going around these first 3 steps of evaluating what the risks are, who are the vulnerable people, where are they, what are the vulnerable assets, and how might that change under climate change. And then you go around that circle and you think, how can we start to adapt and manage those risks? Complicated process, and I'll give you one quick example of that, but then you can implement those, you can monitor how that's working out, you can take on new information. It's a cycle of using new information, continually assessing what the risk, and making adjustments. So here's just a quick example. This is Newcastle city centre. You can see the River Tyne just looping the bottom there. We've got some colleagues who do really detailed models of what happens with flooding. So you can see here they ran a storm in their computer model, and those dark blue areas are areas that flooded, lighter blue areas are levels of flood depth. So you can see they're starting to identify with their models where the risks might be. And you might ask in terms of damage to infrastructure, it might be loss of life, number of properties that were inundated by floodwater, or people, or some wider sort of economic analysis. There's no one way of defining risk. But with these models, what you can then do, you look at a particular location and start to say, okay, what happens if we make some of these interventions we've talked about? So here, again, think about Newcastle, 30-minute storm going across the bottom of that graph. And what the line shows the amount of water depth. So with time, as the storm goes on, the water depth at this particular location is increasing, the flood is developing. So you can see that blue line is the current land use that we've got, no storage of water. But we can compare that, we can put into the model, okay, what happens if we allows us to store water on the roof? And you can see here, the flood depth actually decreases because we're actually slowing down the water getting to the surface by storing rainwater on the roof. What happens though if we do some new development and we build a load of more impermeable surfaces? You can see here that actually increases the flood depth. So if there's some new development that paves over even more of the area, you can see that's going to have an adverse effect. So we can test out these various different options. So you can see the bottom one there that really, in this example, has a big effect, is where you put in things like permeable paving and combine that with being able to store water on the roofs. So modeling tools are really useful in terms of starting to assess how these climate changes that we might expect, how we can adapt and what changes we can make. But some of the key questions are these adaptations feasible? With mitigation, then don't cause increases in emissions. And are they robust to some of the uncertainty? So one of the popular types of responses is what called no regret options, or events or adaptation benefits. So if you think about addressing flood risk by putting in some green space so that it allows the water to drain away better than the surface, that actually has other benefits because it creates a space that people can use. It's potentially improve health, they can reduce air pollution. So let's think about what are the other benefits that we can get from some of these adaptations irrespective as well. So just the final point really on adaptation is, you see there, mind the gap. We actually have an adaptation gap, both at a global level, you can see from the UN report there, but also from the UK Climate Change Committee. From the latest 2023 review of adaptation, they've said limit of evidence of adaptation at the scale we need to prepare for the climate risks facing all aspects of our society. So the gap between adaptation and risk is actually increasing as adaptation action doesn't keep pace with climate risk. So lots of needed focus on reducing emissions, but we do also need to think about how we adapt to address some of these risks. So just going to finish there. So just really very quickly then some conclusions. So I've talked about future changes in climate, and including rainfall is supported by these 3 lines of our observations. There's good physical reasons for them, and also from modelling studies. Kind of the big headline, UK, wetter winters with drier summers, but a greater intensity of summer storms, and a greater amount of rain for the winter. And whilst action on emissions is important and it will enable us to avoid the worst of climate change, failure to do so will require more adaptation. So we don't need to, it's not an either or, we need to do both of these things. We need to think much more holistically. The final point really is that we need to avoid lock-in risk. So when we're doing, for example, new developments, don't try to think about, are we building on a floodplain, locking in future risks. So try to avoid doing that. So I think that sort of covers, hopefully that's addressed. I'll stop. I think we've got time.
Yes.
For discussion.
Yes, thank you so much. I thought that was a presentation, Stephen. And I've certainly very enjoyed and learned an awful lot from it. So we go over to giving people a chance to ask some questions. And I've got one hand up from Peter Lord. Over to you, Pete.
Mute. There you go. Thanks very much for that, Stephen. Much appreciated. I was wondering with the modelling, if or how you could validate it with actual data. For example, can you look at models you produced a year ago and see how well local floods, a few weeks ago?
Yeah. In terms of the climate models, first of all, model validation is a big thing that they do. So what they do is they use all our historic weather observations, and they run the climate models for a historical period and then check those against our observations. So are the models reproducing rain where it should be? Are they getting intensities? Similarly for temperature. So there's that aspect. So that is done, and there are strengths and weaknesses of the models, which again is it's out there and it's published, and happy to talk about that. But yeah, in terms of the flood models as well, so there's different techniques that people use historical events through, and what they need, good observations of what was flooded and where. So people quite often after a storm will go out. There was various projects, for example, going out when there's been a storm and looking at where there's debris from flooding, to try and validate, what sort of it can be quite difficult to do because you do need to capture what actually happened. But yeah, that is an exercise that is undertaken.
Thank you. Then over to Pete Colley. We can't hear you, Pete. I can see you're unmuted, but I still can't.
Sorry, does that help?
Yeah, that's better.
Yeah, given that the UK achieves its global emission targets and other countries don't, the UK contribution to emissions is pretty insignificant. Wouldn't it be better to invest the money that we would have spent on reducing and move all of that money, apart from any money that would generate profit from reducing global emissions, and invest that money in adaptations?
I think, and this is where you get very much out of the realm of science, and this is where it becomes sort of a political and economic argument, and you can have various opinions on that. And obviously, one view is that we should, having been large historical emitters, that getting rich off the back of should show leadership on this, and we have a responsibility to do that. And and if we don't do it, how are all these other why should they? So there's that argument, but it is about we've got ourselves into a bind, really, haven't we? There's no zero cost option here. We could think about climate change, but we're going to have to spend then a lot on adaptation to account for that, which, as a relatively rich country, better place to do that perhaps than many other countries. So, but again, it's some of these knock-on effects of climate change, again, we can spend the money on adapting here, but some of the, can we insulate ourselves again against some of the climate change? So perhaps some of the migratory effects that we might see, migration from some regions, that we can't, how that's an issue already, again, but if we get some of these climate migrants as well, that will, we can't immunize ourselves against that. It's going to be a big issue. But again, that's where it becomes political. I would argue that we do need action on both. We need to take our role in reducing our emissions, and there are other benefits of doing that. But we do have to do mitigation and adapt.
Thank you. Ian Hawker.
Yeah, thanks, Stephen. In terms of the modelling, are we using the same kind of models for short-term and weather prediction and longer-term climate prediction? Are we using the same set of models, or is there a totally separate set of models?
There's the same principles are going in. It's essentially in a sense they are the same. So some of these global models, but they need to, when you're looking at sort of century time scales or the next 50 years, there's other things that you need to take account of that you don't for 2 or 3 days time. So I mean, the example very high resolution models that are used to model these intense storms, they're basically the weather forecast models, but to do a climate change experiment. So they've all got the same fundamental physics in there. But then sort of globally, of course, our weather forecast will come from sort of UK modelers. But then there's modelers, for example, at NASA, there's the Australian Met Agency. They all have their own different climate models, which are actually different. They've all undergone, again, based on the same fundamental physics. There's different ways you can represent some of these processes. So this is where you get some of the uncertainties in the climate modeling.
Yeah. I was going to ask AI to help with the modeling, because of the complexity involved, are you making use of artificial intelligence, to recognize patterns, that sort of thing?
I think it's starting to see that in the literature. I mean, it's not sort of fully developed, that parameters for models and things. I think it's going to be, it's something that's just really, you're starting to see that now. It's not my definitely starting to see papers coming through where talking about how can we use AI to do this. So yeah, I'm sure it will. Yeah.
Okay, thank you.
We're not going to escape AI in most aspects of our life, it seems. Yeah.
Okay. Then we go over to Peter in Newcastle.
Hi, Stephen.
Oh, hello.
Thank you for an excellent talk.
Thank you.
I'm a new boy, change. I only became really interested in about 2018-19. And I couldn't believe our station was considered to be a good thing for the climate. And the reason for that is that it was importing pellets from Canada. And so it was carbon trading, carbon offset, whatever it is. And I noticed on one of your slides, you were putting down carbon trading as a positive. Now, to my mind, I can't, apart from the politics of it, I can't see that it's positive. It's still CO2 being produced by burning wood, essentially.
Yeah. Yeah, no, I probably should clarify that. I don't see it as a positive. It's just carbon trading is seen as a tool of mitigation. I mean, I agree. You've got to look at the total level of carbon mitigation, and the whole carbon accounting thing. I think there's, when we see emissions, we're actually farming out a lot of through our imports as well.
Yeah.
So it's defining the boundaries of what is our emissions and isn't there's a really grey area there. So yeah. Carbon trading was more of I wasn't sort of judging whether that's a positive or negative. I'm probably sort of with you. Don't think that's the problem. It's just shifting it around and perhaps a bit of an accounting exercise. But it's something that I've just put it up there. Something that is.
Thank you very much.
Yeah.
Thank you. Then over to Richard. I've got quite a lot of hands up, so if you all could try to keep your question as brief as possible, please. Richard Tamlet.
Good morning. Thanks for a nice lecture. I don't understand why Wiltshire Council allowed 750 houses to be built in a floodplain. Is that not madness?
Well, yeah, I mean, that goes to the point you say, we've got to start thinking not just about the hazard, but about the risk and the exposure and what we, so that's a good example of the lock-in that I talked about. So they're going to build, a housing estate on somewhere that, I don't know, historically flooded. I don't know the area.
Absolutely. And the developers are saying, can we put additional pumps in to get rid of it? But it's below the floodplain at any rate. So where can you pump it to? It doesn't make any sense at all.
Yeah, no, I mean, we've got to start thinking about not just the hazard, but the exposure and how that plays out. They maybe as part of I think there are, I'm not sure what the potential legislation is on, as developers, what protection they have to put in to protect against flooding. But yeah, it just seems that it's not the best solution is to put a whole new housing development on a floodplain, because you're then going to have to spend more to address.
Absolutely. Thank you very much.
But yeah, it's competing shortage of homes, and you can see where the pressure comes from. And it's, again, what's really challenging about climate change is that there's so many different competing and pressures on different parts of the system, and it's a problem.
Thank you. Then over to David.
Thanks very much. You touched on the economics of one aspect of climate change, flooding. Just one specific thing. Well, the costs seem relatively modest compared to the obvious human costs, but and I also wonder whether those take into account the loss of soil and fertility from floods. But the main question was the wider economic costs. I think it's 20 years since the Stern review came out to look, which gave sort of estimates of up to 20% of global GDP being lost to the effects of climate change. Have those estimates been made, and are people thinking along the lines now?
I mean, I think you make a good point about how, again, it's this point about how we assess risk and damage, pound or dollar value on it doesn't fully capture it. I mean, some of the big effects we see from climate change, from flooding, people and on their lives is, if they have to evacuate and can't access home, is mental health effects. There are severe mental health effects on individuals if they're lost out of their home for a period of 6 months or a year. The property has to be, remade habitable. So I mean, they do. I think some of this data in the report I looked at, they do look at direct. Yeah, I'm just looking at that graph now in terms of damage. They look at direct and indirect effects. So they try to think of it in terms of some of those knock-on effects. But I don't know to what extent they, like you said, in terms of soil degradation, whether they, try to quantify that effect, whether the effect on people's health is proper, how that is accounted for. I think risk is actually much more difficult to assess, and than sort of climate. Then you can measure depth, you can measure extreme rainfall, but risk is much more difficult. But it's definitely, I think, moving towards a more holistic approach to assessing that. If that answers your question, that's what moving beyond what was the damage to a particular building. But I think a lot of that is because information, because insurance companies can quantify the damage to a building, so it's a relatively easy way to measure it. But it's not it's not the, like you say, it doesn't properly quantify the effect on individuals and on society, which is much more difficult to measure. So I think that's the problem in sort of meeting what you quite rightly raise.
Okay. Thank you. Then we go over to Paul W. You have to unmute, Paul.
Yeah, thank you very much for your talk. It's very interesting. one of the big problems I'm having with climate change deniers and people like this is they're saying, well, there's all these natural processes that bump the CO2 up. But is there any modelling of how much CO2 we're actually producing in terms of, for instance, industrial output? And when you add that to the natural stuff that we're monitoring, like the volcanics in the background, do the two add up pretty closely to what you're seeing in terms of the CO2 increase in the atmosphere, minus any kind of sinks, of course, like the oceanic feedback? Is there a very good numerical correlation that A plus B equals C in that respect, if you see what I'm driving at?
Yeah, I mean, it's probably not quite as pronounced because, you know, some of these things are very, very difficult. Again, it comes down to measurement. I mean, I could give a whole talk about how you measure rainfall and how our rainfall measurements are not totally precise. And again, with something less tangible as carbon. But there are certainly, yeah, papers that, you know, do assess this. What's the point I was going to make? It's gone out of my head.
We must have some idea of the amount of carbon that's come out of the ground effectively. We've drilled for, we know how much coal we've done, and we know roughly what the conversion process is.
Yeah.
So what I'm driving at is, you know, one way to defeat these climate skeptics to a large extent is to show exactly that this increase is down to humans. And then, of course, you move on to the further analysis of, and this is what's going to cost in 5 years' time or 2 years' time or 10 years' time if we don't fix it. And it's always that driver that will force some change now. Otherwise, everybody parks it for the future, don't they?
Yeah, I mean, there's certainly people, there's research out there quantifying each of these components and showing how much carbon is transferred between these different carbon stores. And essentially the big whole is satisfied by our emission. You know, that there is carbon budgets that you can refer to. In terms of the drivers, you know, people do say, like you said, it's natural. But really, you know, for me, that doesn't sort of cut it, because it's like waving a magic wand. I'm a bit of a geek. I'm a big Doctor Who fan. It's a bit like an episode where he gets his sonic screwdriver out, waves it, and solves the problem. You've got to identify, if you're saying it's natural, okay, what is the cause of it? So one of the other examples is often, oh, it's all due to solar activity. But, you know, we've been measuring solar activity for some time. You know, we can do these attribution studies, and that doesn't add up. If people are going to have to say it's natural, they're going to have to, you know, where is the science? What is the very specific natural process that is accounting for it? And that's the big gap. I mean, if somebody did that research and demonstrated it wasn't human, of course, then obviously I think they'd be a Nobel Prize winner, because that's really going to crack the problem. But, you know, those attribution studies I referred to point to driver, and as you've said, these components and transfers of carbon are measured. There's uncertainties. There's always error bars quoted on them, so they quantify these stores and the movements between them, and there's always error margin, so it's not quite A plus B equals C, but yeah, that works there.
Yeah, thank you very much. I think when it comes down to fixing things, it's down to largely the biggest lobbying is probably the insurance companies, isn't it? Because it's either people that suffer or it's insurance that pays for it. And at the end of the day, it's spending money now to protect the future, isn't it?
Yeah, some of the
only driver for that is both education and insurance companies, who ultimately pass the cost on to us.
Yeah, I mean, insurance companies are sort of some of the big drivers behind taking action, because they're at the front end, they're seeing the claims coming in from these you know, increased events. So yeah, they're definitely a major part to play.
Okay, Neil Allen, please. You're still muted. Oh, no.
Yeah, is that okay? Yeah, I mean, I've been involved in this for about 30 years, and so one of the about when you were talking as well, Stephen, was that 4 degrees. I remember 20, 30 years ago that people were very concerned about 2-degree rise. It now seems to be a situation in which we are accepting we've moved beyond. I mean, I remember 30 years ago that 1 degree rise was the thing that we were talking about. We were trying to actually gain. It moved to 1.2, then 1.5. We got the Paris Agreement and so on. But risk assessment that you're talking about, that has that actually been implemented in politically to any great degree? Because the big problem over the last 30 years has been the fact that politicians did not move much away from the business, comparing things with business as usual model. Their economic things were costs against business as usual. The future risk had been for virtually all of the COP meetings that I went to and things. So is risk being taken more to task, and are people really talking and the politicians talking about risk sensibly now?
I think they're starting to. They're probably not there yet. I mean, it's like in the COP, there's a lot of focus on risk through the loss and damage discussions on a global scene, and the national level, the whole idea of doing this climate change risk assessment, which they obligated to do every 5 years, is that we do prepare, but then these periodic updates to Parliament, and I give you sort of a quote from 2023, shows that while we're starting to get a handle on what these sort of risks are, and we know some of the adaptations we can make, but there is a block to, I don't know what that block is, whether that's sort of finance, I think it's more sort of structural and institutional. So I think there's an increase
to be attitudinal. I mean, in essence, there's been an attitudinal change. I suspect politicians don't like risk as and I don't think that is actually altered very much. Can I just ask you a very quick thing about whether there's also been much talked about changes in Gulf Stream and whether that is whether dimensions and the movement and so on, and the other bit was about the jet stream, since both things are going to affect the climate in our particular area. Has there been much happening on either of those recently?
There's a lot of research happening now on the jet stream, because obviously sort of particularly important for the UK, because that's a big shaper of our weather. But it's one of the aspects that the climate models are a little bit less good at. So with lots of these studies, any paper to get published, you've got to talk about what the uncertainties are in it. And so there's some of the uncertainties are on there, but there's a lot of research now starting. People are really starting to look at some of that in have been. I'm not so much sure on the Gulf Stream as to how much is happening on that. I know the popular scenario sort of shutting down of the circulation, which is
the redirection, and that would then radically affect the UK. But I mean, it doesn't sound as though it's moved on then. It was really 15, 20 years ago that was very much a major concern that affected you at the time.
The latest sort of I was reading, and again, it's not because it's not where I research, I don't sort of focus on keeping on top of it, that sort of scenario, complete shutdown that triggers these huge climate changes and we actually get a lot colder, is actually a very unlikely event. It's it's potential, but it's not really something that's considered a plausible or a likely scenario.
Okay, well, I hadn't heard anything, so I assumed it had died that sort of death. Okay, thanks.
Peter Weston.
Thanks, Reen. Thank you, Stephen, for a very good talk. I'm going to ask a question which is a bit nasty in many ways, but I'm going to ask it anyway. I have personal responsibility to reduce my energy CO2. I regard it as a moral responsibility, full stop. Okay, simple as. Now I'm left with the next issue: how many other people can I influence or not influence in that process? Now, the one issue which I influence most of all might be the political level. Now, I don't want to get into an argument of whether we mitigate or. A simple issue is we made a commitment by 2050 is carbon neutral. Now, my master question comment now is, what points along the way would you choose to monitor this progress in such a way that I can say to the politicians and everybody else, we're not going to hit it? What would the parameters and the metrics that you would choose, top 3, 4, whatever it's going to be, to say, yeah, we're going to get Because there's lots of debate whether you're going to get there. It's a hard question, I know that. But what would be the 4 metrics? A handful. Desert Island Distant type question. What would be metrics you'd put along the way, please?
In terms of that we're not going to reach the target.
Whether we're going to get 2050. Yeah, 2050 is the target. And we've got 27 years to get there, 26 years to get there.
Yeah.
So what are the metrics along the way?
I mean, one of the key things that we're starting to see is that the global temperature, we're starting to, we've got this target of 1.5 degrees. We're already seeing individual years and around 1.5 degrees warmer. So
I don't care about that. That's the whole world. I'm talking about the UK. I'm talking about the UK government. Okay, I'm talking about what should I expect my political leaders to have as the thing. They stand up in front of us and say, "We're getting there. Here's how we're getting it." What would be the metrics we should judge their performance? Our performance on.
Yeah, I don't know what's going to work with politicians. I think we've got to look at our level of independent. The Climate Change Committee is independent, and then they are producing a lot of this information, and that in terms of adaptation, they're saying these metrics are already out there. They're saying we've got gaps from where we need to be, and similarly there's these periodic updates to net zero, the targets and the emissions, and they periodically will in the UK talk about the emissions gap. Now, I don't know whether we need to think about sort of an approach that more relates perhaps to individuals rather than these large scale metrics, because to the average person in the street, national levels of emissions don't mean much. So maybe we have to look at metrics like some of the things we talk about, incidents of flooding. Can people relate to that better, or is it health outcomes? So when we get increase, we're starting to see some 80-degree temperatures that we saw in the UK some time ago, was it a year or two ago, were really unexpected. We didn't expect to see that from the models for some time. So if we can, I think relating it to impacts should drive politicians, and what the appropriate metrics would be, I don't know, but I think something that more relates, that they could relate it to, the impact on the health service and things like that. But I think
it's a community. You see the issue I'm pointing to. It's a communication issue.
Yeah, it is. Yeah, essentially
a communication issue. I'm trying to ask your opinion as somebody who's really steeped in this stuff. What would because it's a long-term thing. It's not the weather tomorrow and not a year. It's all irrelevant. What matters is this trend, which we're underlying trend, and how would we communicate to people? This is serious. The gentleman said earlier on, you don't want to bother climate skeptics. It's a waste of time. Yeah. Basically, you really got to concentrate. What do we need to do? Even you can't look at the rest of the world. You've got to say you can't do anything else except your country, and what we can do in our country, and what metrics we can have to be a leader. So we say, is it a simple? Each year you say somehow or other we've reduced our output of carbon by X amount. Is it a simple figure like that? We're quite used to having quite complicated figures summed up in one figure. For example, cost of index, CPI. Yeah. We're used to companies who do lots of diverse things. Each year is a profit or not. They're judged on that. So we are used, as far as climate goes, we don't have kind of metric to get our brains around in some way. That's what I'm after, really.
I mean, those national level emissions are sort of reported, but they don't I like the analogy that you said with the CPI, or with unemployment figures or inflation. I don't know whether it's just a matter of getting the profile, because those annual emissions data, they are reported as part of the the COP arrangements. Whether it could be I guess the problem is in terms of getting out into the headlines is that it's not very relatable, and I don't know how you make that so that it relates, people can interpret that, because we can all interpret the cost of inflation. It's a nice simple percentage figure, and we can not budget do the same with the unemployment figures, and I think the information is there as to I think you're right, it's about communication, but I'm not I'm something I'd have to think about as to how it's a good question about what would be a high profile nicely communicable metric to really measure and measure government progress. There's lots of ways they do, measure, but that is out there, but it's not getting the headline figures.
Okay, thank you.
Okay, thank you. May I suggest the annual total insurance payout would be an interesting figure to have that year to year. It's for inflation to see where we're going, maybe. Anyway, over to Barry. Barry Zussman.
Oh, thanks, Reen, and thanks, Stephen. That's great talk. Just want to go back to a concept that you introduced quite early on in your talk about these natural cycles. Natural global cycles, and a couple of other questioners have brought it up as well. I want to ask you about El Nino and La Nina. It's El Nino's in the news, of course, because we're told it's going to be a major El Nino year, and I'm just wondering if that cycle El Nino La Nina is a predictable cycle, and or if it's shown that the cycle itself is affected by human activity. Because if that's the case, then obviously predicting in the future is going to become vital.
Remember rightly, I think it's one of the uncertainties is how El Nino will be affected in the future. I think that's a bit of a source of uncertainty. And it's the same with lots of these sort of teleconnections, and there's research goes into that, but we don't have a definitive picture. There are other less well-known ones as well. There's one that affects our climate called the North Atlantic Oscillation, which is due to the pressure differences between, that's something you've heard of. But again, some of these changes in these connections are, there's a lot of research goes on to that in understanding how these will change, because they kind of have you've got the long-term pattern of change. So talk about temperature, it's much more simple. So you have this increasing trend in temperature, but then you get these years where you have El Nino and the temperature rises a bit, and that's so these changes are superimposed obviously on the long-term trend. The situation with rainfall again is different because it tends to be less global and much more regional as well. So it's really difficult, particularly if we're interested in impacts, is the fact that these things are much more regionally based as well for rainfall. So that adds an extra level of complexity. So there is a lot of research going on to how might things like El Nino change, because it is some of these natural processes, these, as I say, the teleconnections are really important parts of the natural variation of climate that interact with the changes that we're making.
Thanks, Stephen.
Thank you. Okay, the last question for today is from David Rogers.
Oh, hi, yes. Thank you, Stephen. That was a very interesting talk. I've just got a question about something that was in your slides and something you hear quite a bit about, and what your opinion is, the business of carbon capture and storage. Is it a realistic thing? Is it really happening? Or is it just greenwashing?
I think that there is a lot of research. I mean, there's colleagues here in the university who are doing lots of work looking at carbon capture and storage, and I know a lot of people who would argue is that's the only way actually that we're going to be able to actually achieve these reductions, because the rate of change of society in terms of reducing our emissions, there's all these barriers to making those sorts of changes, and it is really difficult. That there is a body of opinion think that is actually the only way that we can make up that shortfall, and that we can only people would argue we can only get so far by some of the actions of reducing emissions. Now that's just one viewpoint, but I mean it is a legitimate, I would say legitimate area of research, but I think we've not got anything that works on that we need. So right. On the timescales that we need to take this action on reducing our emissions. We shouldn't sit back and think, oh yeah, this technological carbon capture and storage solution is just around the corner. On the scale we would need it. I don't think it's ready yet to solve the problem. We do need to keep on reducing our emissions, because otherwise it'll be too late. By it has a part to play. Definitely, and but it's not, you know, we shouldn't see it as the solution.
No, sure. And yeah, I mean, I've got this, and envisage all this CO2 being pumped into old oil wells or gas fields, and then staying there for a couple of years and then all coming out again. I mean, I don't know how technically valid it all is. I mean, I know there's research going on, but I do wonder how realistic it all is.
Yeah, I mean, a lot of it is based on kind of replicating natural cycles, because the cycle is, rocks are weathered and that releases CO2, and that process, natural process of cycling, of it's trying to accelerate and mimic it essentially through acceleration. But yeah, I mean, that's sort of a lot of these processes are classed as geoengineering, and one of the some of the people talk about seeding oceans and things, or even putting particulate matter in the atmosphere to reflect and manage solar radiation. But there are lots of unintended consequences of some of these technologies that we need to properly understand. Human society, we've got a long history of doing things before we fully understand them. And geoengineering is probably another one. It was over a decade ago, the Royal Society did a really good report on geoengineering approaches and assessing, the feasibility of those and what the potential risks are with those as well. So it's, before we do any of these, we need to understand, are there any unintended consequences?
Yeah, thank you.
Okay, well, thank you so much for the fantastic talk, Stephen. It was absolutely fascinating. Okay. And it will remember all you've said for a long time. And it's great that you allowed us to record it so we can have another look at your slides as well, because they were really good and very useful.
Yeah, if you want me to send you the slides, I'm happy to. There's some links on there that I don't know whether that's something that's useful.
Well, that would be great, because we can we can put them on our website as well, so people can look directly at the slides. Yes, please.
But I'm just going to say, I mean, I think it's great that so many people are sort of engaged in this topic, and it needs people just to go out and have conversations with friends, with family, with people down the pub, and just use your knowledge. Everyone's got a part to play. You talked about communication, and I think you've all got lots of experience and lots of knowledge, and I think it's great that you're engaged in and talking to people. It's really good.
Thank you. Thank you. The goal of this group, really.
Yeah.
Okay, well, that's it then for today. Thank you all very much for joining. Please do have a look at our still very newish website, and if you can, do promote it. It's u3 all is one word .org. On the chat, I haven't had a close look at it, but if you want, you can save the chat function and look at it at leisure. If you can't find the save option, just send me an email and I'll email it to you. If you would like to pose a question to the group for our next meeting, please again email me. The next meeting will be on the 28th of February, when we plan to discuss, to dissect COP28 and look at the claimed feasibility of CCS, carbon storage and capture, David, the holy grail of fuel industry. Many thanks also, as always, to our magnificent bear, and stay safe and take action if you can. Bye.
Thank you. Thanks to Stephen. Yeah.
Thanks a lot.
Right, thank you.